Now we will start with find the integral representing y dx dy z, where v is the volume, by the plane z equal to x plus 1, z equal to 0, and by the cylindrical surfaces x square plus y square equal to 1, comma x square plus y square equal to 4. Since we have a cylinder, we'll prefer using cylindrical polar coordinates. Remember, cylindrical polar coordinates is an extension of polar coordinates of a circle in 2 dimensions. So, we are using the cylindrical polar coordinates. The cylinders are given. Now remember, there are 2 cylinders which are given, x square plus y square equal to 1 and x square plus y square equal to 4. The cylindrical polar coordinates are x equal to r cos theta, y equal to r sin theta, z equal to z. Dx dy dz is equal to r dz dr d theta. Remember, for our cylindrical polar coordinates, we'll prefer using this order: first z, then r, then theta. Now, to get the limits of z, as I've said again, I'll repeat, we'll make use of the equations which contains exclusively z in it. So there are 2 equations which are containing. One is z equal to x plus 1, which turns out to be z equal to r cos theta plus 1 in polar coordinates. And the other is z equal to 0. Remember, z equal to 0 is the xy plane. So, since z equal to 0 xy plane, it turns out to be the lower limit. Since there are 2 values of z, I need one of them to be the lower and the one to be the upper. Xy plane turns out to be the lower limit, and the other value of z turns out to be the upper limit of z. Now, we'll try to get the limits of r and theta. As I've mentioned, I'll repeat. To get the limits of r and theta, make use of the equations which contains exclusively x and y. So x square plus y square equal to 1 turns out to be r square equal to 1, which is nothing but r equal to 1. We won't take into account the minus 1. Check out. This is a circle of radius 1 and center 0, 0, which is nothing but the origin. Same thing continues with x square plus y square equal to 4, since we have 2 equations containing x and y exclusively. That is r equal to 2. Now this turns out to be a circle centered at 0, 0 and radius 2. So these are nothing but 2 concentric circles with radius 1 and 2. Now we'll draw the diagram. The bigger circle, and then we'll draw a smaller circle of radius 1. I'm not that good in drawing, we'll manage it. So we'll label it r equal to 1 and r equal to 2. Now, since by the cylindrical surfaces has been given, that means I am interested in the area, in the volume between the 2 concentric circles. And first we will try to get the limits of z, then r, and then theta. Z ka limits, as we have already got, this is the lower limit and this one turns out to be the upper limit. Even if by mistake you have written this one as a lower limit and this one as the upper limit, the change in your answer will be only with respect to minus. That minus sign implies that you have taken a wrong limits. That means you have interchanged the upper and the lower limit. So don't worry if your lower and the upper limit ka, whether instead of writing the lower you have written a upper and instead of writing a upper you have written a lower. The change will be only in the minus sign. R ka limit will be from origin till the outer circumference. This part is not included, so we have only the annulus wala part. So the limit of my R is from 1 to 2. Theta, since we are including all the 4 quadrants, theta ka limit is from 0 to 2 pi. Now check out the limits of my Z, R and theta are not all constants. Only R and theta are constant. Z is dependent on R and theta. Now I'll be interested in my integrand. My integrand is y. So it turns out to be y equal to R sin theta. So given integral is this, triple integral. Now we'll rewrite in terms of cylindrical polar coordinates. First z, 0 to r cos theta plus 1. Then r sin theta, the integrand y, dx dy dz. R dz dr d theta. R and r gives me a r square. Now first I need to integrate with respect to z. R square and sin theta, all of them are constant. So it will be outside the inner integral. So we are moving r square sin theta outside the inner integral. So z ka limit is 0 to r cos theta plus 1 dr d theta. Integration of 1 with respect to dz is z. R from 1 to 2, r square sin theta which is remaining, z ka limit is 0 to r cos theta plus 1. Now we'll apply the upper limit minus lower limit. It gives me r square sin theta. This turns out to be r cos theta plus 1 minus 0, which I am not mentioning. This is dr d theta. Now we'll open the bracket in the second integral. Now people can observe properly. R ka limit is constant, theta ka limit is constant. If you want, you can write down it as a product of single integrals. R square r gives me r cube sin theta cos theta. This gives me r square sin theta dr. We'll integrate with respect to r and then with respect to theta. R raised to 4 upon 4 sin theta cos theta, r cube upon 3 sin theta d theta within the limits 1 to 2 and then d theta. Now we'll apply the upper limit minus lower limit. The upper limit is 2 and the lower limit is 1. So this turns out to be 2 raised to 4, which is 16 upon 4, which turns out to be 4 sin theta cos theta plus 2 cube, which is 8 sin theta. Now we'll apply the lower limit, which is 1 upon 4 sin theta cos theta, 1 upon 3 theta from 0 to 2 pi, 4 sin theta minus 4 sin theta cos theta minus 1 upon 4 sin theta cos theta is 15 by 4 sin theta cos theta, 8 by 3 minus 1 by 3 is 7 by 3 sin theta. Now sin theta integration will be minus cos theta. Here if you see, you have sin theta cos theta, which multiplied and divided by 2 gives me sin 2 theta. So the integration becomes easier. Now only integration remaining is with respect to theta, which I hope you people can manage. If not, you can continue having a look. Minus cos theta